All right. At the beginning of or end of the very first speech, there was a call out for anybody who wants to build a prototype that can do all of the limitations. This is the prototype. You may need the grant funding in the tip jar with this logo on it. First up, what are we discussing? Well, we'll be talking about the use case, and you requested it. That is Vulkan and the Allen Institute. How does this apply to Semantic Media Wiki? How do you import and normalize thousands of triples that we get from RDF stores? Creating instance pages without knowing exactly what we displayed on them, because I'm not paid enough to type it all in. Embedding Sparkle within SMW templates, and expanding existing instance pages with semantic results formatters, a true PHP view layer, and creating dynamic charts. But first up, what is the Allen Institute? This is a very common question. They are based in Seattle. They're a large building with a bunch of mice and human brains and scientists in it. They were launched in 2003 with seed funding from founder and philanthropist Paul G. Allen. They serve the scientific community. At the center of their mission is all neurological processes and mapping. They generally pull in 2 to 3 human brains. I think they're on map number 3 after 7 years. This is actually a really big website in the neurospace community. I think they're the first people to industrialize the slicing and encoding process. As gross as that sounds. And this is what I found on the website that sums it up the best, and where there's actually a true separation between Vulkan and the Allen Institute. They are a 501c3 nonprofit medical research organization. And while we do mice and lemurs and things of that nature, our true focus is actually how the human brain works and getting a mapping there. But you do have to start small before you go big. And this is the website they run. Different screenshots of it. It is open, public, and online. That is one of their core tenets. It's really, really important to them that any information used is reshared and preferably not modified. It's detailed interactive 3D of the human brain right there, and gene structures there. The genomic analysis of every brain structure, that's right there. And we have high-resolution atlases of the key brain structures, which you can also drill down into them to very deep-level gene sequencing. That little graph there is actually the same gene repeated again and again and again, but depending on where you select in the structure, these reds and greens change. I'm told it's a scientific thing. And next up, what is Neurowiki? So about a year ago, Vulkan and the Allen Institute got together, and we decided to try to crowdsource, it's not a word I really like, but get more people involved in trying to organize some of these gene structures, putting them online. And we came up with the idea of the joint project between the Allen Institute and the Vulkan Project Halo Group to build a semantic media wiki that does large-scale genetic instances. We chose drugs, diseases, and genes. We did take in a pathway store as well. This is a finished prototype, testing the import pipelines and display components for combining 5 major RDF datasets and 4 different sources. And our current planning, we're in the give us more money phase, and that comes down to including complete dataset mapping. KEGG is very, very large, same with Uniprot, everybody's worked with it. There are many, many GEGs that have to be mapped and ran to the LDIF pipeline. Creating a better ontology. This may be hard because the only thing neuroscientists agree on is to disagree on everything. Even when it comes down to genes and what a gene is, that's some of the problems we've had. Creating multiple ontology management by class, that's a really big thing. We do want different classes of user and scientists to be able to upload their interpretation of gene to the mappings. And then we want to import and map these to the scientific papers that the Allen Institute has placed out. A lot of these papers keep a lot of their depth in their captions, and you'll see alphabet soup of gene names and pathway names and disease names. All the diseases you see on TV, those are actually a very small subset of named ones. A lot of them are 4-Tetra T67:. And this is what it looked like when we finished up. you will be seeing the active version of these. This is just my broad overview. All of these are online, and they will be shown. It is open and public as well. Data stores from the multiple data sets. Christian and Andreas will be going through our LDIF import framework. That should answer Marcus's query on how to get a bunch of RDF data in there. The outlines of each imported instance are all embedded in wiki properties and provide views of these RDF sets. They use Sparkle. Nothing in this wiki is actually hand put down. The charting tools also pivot off the Sparkle queries. These are all alternate Sparkle views from the Sparkle result from the semantic results formatter. And navigation and composition tools for mining the data. It's not really useful if none of the scientists can do anything with it. So where did we get the data first? Well, we got it from 4 places. KEGG, that's a Kyoto research place for genes and genomes. They are a very, very large data set of hundreds of different entities. We chose pathway and genes, and we only chose slivers of those for time of import and demo. Disease zone, this is what we use as a large catalog of genes. It has pretty much a very large simplified listing of diseases and genes. Basically names, UniProt IDs, and then we can use those IDs to bind into things like Drug Bank and CIDR. Drug Bank is almost an encyclopedia of what you really want to know about a gene and drug. And CIDR, in America we have these television commercials for drugs, things like My Leg Falls Asleep, and at the end they always have this terrible paragraph of heart disease and anal bleeding it gives you, instead of just getting up and walking around. And CIDR provides all those. So, and the demo of this set is right here. These are the entities we actually pulled in. As you can see, we have about 18,000 we could have made pages out of, if so wanted to. Because of the KEGG pathways were so weird and large, we actually left them in the RDF store, and these were the categories actually imported into our ontology for the wiki. CIDR, our genes, and genes. We kind of got the binding off the gene here, but with these gene bindings, we can use diseases and drugs, and with drugs, we can find CIDR.
You mentioned something about this using Sparkle. Is it like Sparkle embedded in the wiki, or is the regular OS query?
Slides 14 through 17. Coming up. All right, so I did get a question while smoking yesterday. Do we have to use the SMW plus classing mechanisms to build our ontology? No, I actually use Protege. As you can tell, Protege is really bad at making something simple look simple. But this is an exceptionally flat ontology that basically all of your things with just inverse relationships back and forth. It's really simple to do when a drug treats a disease and the disease is treated by a drug, just back and forth that way. But this did help because it gave us a good LDIF mapping for a centralized place to request more information in larger Sparkle repositories. We were building a rough map in our wiki ontology, and then as that map led us to points where we needed more thorough data, we would reach out to the Sparkle resource, usually Drug Bank or CIDR. And what this turned into was those numbers. We were able to decompose these entities into this ontology using LDIF. And that created a total of, am I off my slide? 61,000 different pages we could create. But, in the interest of time, this ontology came down to looking, the nice ontology browser. Say we choose a gene. Let's go to AASS. And you'll see it actually pulled in these information, like location mitochondrion. We embed Go processes into Go functions. These are important to the gene researchers. And on top of that, essentiality, is it essential or not? Along with the label we build the pages off of, and subnames for the gene. These are all ways that scientists can reference that gene. So I'm only going to briefly touch on this because it is the 30 minutes after me. But this is our import pipeline. The 2 points I really want to put out are R2R and Silk. R2R is a mapping tool that takes the RDF store, we apply mappings to where it fits in the wiki ontology, and it does that translation into our system. Silk, on the other hand, finds duplicates, diseasome and drug bank. They have, one of them is a subset of the genes, but they aren't referenced the same way. So you generally have to find things like the Bio2RDF label, the Unipod ID. This is what finds those links, merges the names, and creates single entities. And after it was all done running, our 32,000 that we were able to map, and these properties turned into an actual about 20,000 uniques. Unique instances, yes. So, with that done, I now had about 20,000 pages I could create, and that would be horrible. So, we had to write a bot that does this. RT, let me show the numbers, there we go. So the big thing is fetching our RDF dumps. These were run on D2R servers. There's been interest in that mentioned. I believe Anya will speak to it a little bit. Next up, I used the regex script, which basically just grabbed the labels out and tried to normalize them as best as possible, exporting them to a list of page names that you created. Open up our category-specific text file, gene, disease, or drug, and all it had in it was in text was wiki markup, 4 template includes, because I didn't know what was going to be in those templates. And then we contacted Neurowiki with the MediaWiki Gateway RP framework and sent out the page request. This created our initial set of pages. There was one large bug, which is mentioned at the end for that. It has to do with those drug names.
You use label as wiki page, right?
Yes, we use label as the wiki page, and we also use the label as a binding to what category it sits in. So it knows that the label AASS is a gene, and I also use that as the page name for it. And I wanted to show an D2R dump real quick. How this was fetched is, this is D2R running a translation on the diseasome database, and by curling that link, you get all the doubles, or you get all the labels for this page showing. And for those of you who haven't seen one, this is what it looks like running on the front. So, this is about what I came up with. This is a standard wireframe, but when I was creating these pages, this is the gene page. I basically had 4 base templates for each entity type or category. So for gene and number 1, that was our info box. I used that to store visible inline properties. So turning our RDF data in, there's sometimes just trillions of ancillary fields. The ones that were important for other widgets and searching and other wiki tools, they went in here for display. The outline view, if there was a text block, some of them more than others, they would go there. My widget template, if your manager is anything like mine, after you're done, you get a bunch of requests. They go right there. Up next was the broad table Sparkle queries. This is where most of the embedding took place. You'll see these in the accordion view on the final site. And then our hidden inline properties. There are quite a few things that researchers like to search on for, say, the faceted search that do not need displayed on this page. I usually threw them down here blind and then ran the repopulate on the page, and they appeared in all of our nice tools and the invented pieces that we came out. We were trying to make this work with all the tools as well. All the tools were already available for SMW as well. And this page looks like AR, the androgen receptor. So this entire section right here is all one Sparkle query with a special formatter. This is our widget page. And this is, say, our side effects page, our effects page. So these are the side effects associated with these drugs that affect the androgen receptor. Finally, So I finally got to the point where I was able to get Sparkle in a template. But when it comes down to the graphs being displayed, well, very nice, and all the work done for them is wonderful. They don't actually capture the data in a way that's very meaningful to neuroscientists. So we had to write our own. We eventually got to the standard results formatter after we did the embedding of the Sparkle. We call it contacted our onto-rotor triple store. And if anybody has ever worked with the code behind the semantic results formatter, you get a very odd data object. And that's fine because Sparkle returns a very odd graph. So the coding behind that, we actually adopted a strategy pattern where each one of those, say, donut graph versus bar graph versus stack graph, has its own class. And we usually branched off that whether we were doing a gene or a drug or a disease. And then we included the Smarty processor. Smarty is a PHP view engine. Yaron actually used it in Wiki widgets, or media widgets, Wiki widgets.
Oh yeah, I didn't write it. I just maintained it. It was certain.
Well, whoever wrote it needs to take it out because it took me forever to figure out how to turn it off. And they only use it for a variable. So it's in there. This actually takes, I broke the fourth wall with the wiki and the fact that these formatters are not available on the wiki page. You actually do have to go to the server and write the code. These are .tpl Smarty files. So I do the massive sort on my Sparkle results. I give them to Smarty, and it fills in a very blank-looking form of what gets injected into the wiki. So you'll see one of my templates is just JavaScript embedding, which goes to the head, which turns on a graph. Another one is a block of HTML, which forms the outline view. Which leads us to what Joran asked about. Embedding Sparkle semantic results formatters. Every piece of content on every instance page comes from a Sparkle query. Nothing that you saw on that AR page was handwritten. It was all inferred from our RDF stores. Secondly, all the inline properties are embedded in the templates returned by the Sparkle formatters. So I actually had to build a wiki page that populated itself, that re-added variables to the semantic wiki side of things, and then that comes to a bug later. And next, all three of the types of dynamic graphs are interpreted results by Sparkle queries, and they are JavaScript injected into the head. And then the outline template takes selected predicates and objects from a Sparkle query, defines them, because I'm basically just asking for everything in the data store. I select the predicates and objects I want, and then I put them into our HTML template. And what that looks like is this. As you can see, it's the ask with Sparkle sub in, our query. And this is me saying, I want these predicates allowed singly, which go into the top of the outline template. And I'm saying that I will probably have multiple values come back on these, so put them inside of a group to output. And as simple as that. Which comes to the not so simple part. What do the Sparkle queries mean? So, this is forming our outline view. For those of you that don't read Sparkle, that selects a gene from a set of 3,919 in diseasome. As said, diseasome is actually an extremely generic dictionary that just says these diseases exist, or these diseases and genes exist. But Drug Bank has a much more thorough set of information. And it attempts to find much more using the bio to RDF symbol. You can use Uniprot IDs, you can use Ascension IDs. We skip that for population speed time. A lot of those IDs require Uniprot. It's the main key binding for most genetic terms. And what happens here if this optional fails is actually an edge case where we get this blank page. That's what happens when one of the genes that is pretty much undefined, somebody found it in a brain of a mouse but didn't have any interest in it, so documentation is gone, if ever even studied. You get these blank pages. And yes, there are a lot of them. And this is an example of how those donut graphs got populated that we were displaying. This one builds the inner ring of the donut. moving drugs, gene targets on the drug to the organism. So you'll see a circle that says this affects humans, or this affects mitochondria, or this affects bacteria. And then secondary, we get the side effects of those drugs. So you'll actually see the genetic group in animals with the most side effects applied to them on the outside circle. So, in the end, our final application stack came down to Neurowiki, the LDIF import pipeline, semantic Neurowiki, and SMW+. This is a small piece of the extensions. Most of them are relatively standard. They come with the SMW. The big one was our data import, Halo, enhanced retrieval. Wiki tags was actually, if you ever worked with scientists, everything is in spreadsheets and text files. So this is Jesse's application that reaches out and puts these in your email and text documents and Excel documents. You can actually talk to the wiki and highlight what's going on. And then the view libraries we add. The only new one I think anybody would be unfamiliar with is HighCharts. That's the that's the Flash library that was producing those graphs. All right, so our bugs, bottlenecks, and unexpected features. First one was this. Those RDF labels that come out, a lot of them look like that. They have ascension numbers and special cases added that kind of dictate where the set is. That's actually a nice looking one. A lot of them have HSA colons or all kinds of unique identifiers. So it's really easy to get 6 digits off of them, but it gets exponentially harder as you get more data sets in. Secondly, here's one of those fancy drugs that is unnamed, probably because they haven't got that much to charge for it. All these, those actually break the URL naming schema of pages. So until we find a way to interpret in and out of what that means through the URL schema and the name, we're kind of locked into that one. Certain drug compounds are pretty much working as massive blank nodes. Calcium, it's in everything. So when trying to build a circle of creatures it's in, they leave nothing so we don't fill up our triple store. So we had to deal with these 2 blank nodes, and I'll show you in action what that looks like. And then the page create bot. One thing we noticed was by embedding those Sparkle queries within the templates, that even doing the refresh data and the maintenance directory did not go deep enough to register our inline properties for the other extensions. So after I got the pages created and the templates populated, and we knew what was in them, then we had to run a re-edit on all of those just so they got saved deep enough that our other extensions would turn on. Faceted searching was a big one. And let's see it in action. So I'm going to sit down and show you a couple of different browsers I have open. One of them is the chemotherapy path. That was the interesting thing I found. I was able to find the drugs that are actually used in chemotherapy just by looking at our graphs. Another one is the dangers of propofol. How are base entities like calcium represented? We have searching, and mainly this segues into, do the existing extensions work with the framework? So, let's do chemotherapy first. All right, so we're starting out with breast cancer. Down. We see it's part of the AR, the androgen receptor. Oh yeah, you can get some interesting things there. You don't want to look at the HIV page. Now the reason this androgen receptor is the only one named, this is an example of only one gene appearing in both the diseasome and drug bank, while all of these other ones were unreferenced and we'll need to find a deeper data set to be able to add information to them. Coming off that, we find our drugs related to breast cancer. There are lots of them. And these are the different pieces of things they do. But what I'm interested in is the side effects to breast cancer. So we have all kinds of horrible things that happen to you taking these drugs. Now we know the ones that have the most horrible things. There's one. There's one. So that leads me to the AR page, or one gene. You can see it's cancer-related, endocrine system, muscular, and our side effects graph shows us that nimultide and bicalmutide, I'm guessing those things are chemo drugs because the only things that cause you to almost die is chemotherapy. Which leads to the nimultide, and you'll see nimultide is in primary use in the treatment of prostate cancer. It attacks the androgen receptor, which is basically what all of our pages just read off. And then bicalmutide is pretty much the same thing, non-steroidal anti-androgen for prostate cancer. So
It's not generated.
it's generated from the RDF store. So in our RDF store, I believe, yeah, mechanism, this is description, you'll see mechanism of action and pharmacology. And yeah, I just chose ones that got populated really well for the demo. Some of them have one line, some of them have no pharmacology. So running off that, we've learned that things that cure prostate cancer also cure breast cancer. We've actually found some very powerful drugs that you should never take because they kill you. And we have the graphing of the different disease classes, cancer being one, endocrine, prostate. So that was my biology 101. I didn't really learn much about biology, but putting this together has taught me that much. And then the edge cases. Here's an example of one of our calciums. As you can see, it didn't bind to anything because it's everything. But we did know that the two disease ratio types by class, disease affects bone and skeletal, which is where calcium is. And last up, let me show you searching. Here. So AR is in almost everything. I'm looking for the gene, which knocks this down. Location, was it the nucleus? Yes, it was. And there we have it. And that's proving that we've actually been able to drill down through our included properties of location. Location only came from an RDF store. I embedded that in this box. So that's an embedded property. And this is what it pulled from the RDF store and their embedded properties. And we can go to the page and do all that stuff too. This works for the diseases and drugs as well. This is the somewhat public opening of the site. So if anybody wants to mess around with it, I did make a nice main page that has all of our test cases here. You can go play around and click through. And finally, I have the entities in the store that I added if you want to see the current status of population or where the project's at or where the current state of the site's at. And now it's Christian's turn to tell you how we got all these wonderful things in here.
Quick question maybe. Is this an output-only wiki? Can people interact with the content and change things? Or?
It's output only in the fact that for the dynamic sparkle in those pages, there is certainly nothing stopping you from making genes I like, writing your own sparkle queries. Good luck.
The design requirement, though, was that the data which we were pulling from the standard stores not be changed.
Okay.
That was,
Or if it does change, it'd be a
so you can add new things to it, but the actual data, you can't say, oh no, keg is wrong here, I'm going to put some of my own value in it.
But I could copy something from another wiki and paste it there somehow, and it just wouldn't end up in the store, but it would stay in the wiki.
Oh, exactly.
Oh, yes, that's certainly correct. And in fact, there's a whole part of this use case which has to do, which Will didn't go into, which has to do with how a scientist would then contribute a data set into this.
Yeah, they really want to be able to haggle over what's on the page, and that's where the input slide would come into.
Thank you.
Do you know the Wiki Project? Or was that Wiki Professional at some point? I I think it's pretty dead now, but it used to do pretty much the same thing in 2006, 2007. Maybe you know R and bonds.
I'm not sure.
Which project was it?
I was Wiki Professional and all of his umbrella. Baron Mons, yes. Familiar? Is there a question or a follow-up?
Basically, I was just wondering if this is at all related, or if there are any contact with experiences or are exchanged and stuff like that.
It would have been nice to, because we ran on this one around.
Yeah, so no, that, we didn't, we weren't aware of that.
And
There's overlap, but you'll find everybody has some overlap in this space. The neuro focus here is anything a big difference from what he's doing.
Yeah, but on the unit mapping, what I worked on for that was mapping, using unit to map stuff to Wikipedia, coupled with information about proteins and drugs from Wikipedia.
yeah, I would add, while we ended up in the neuro domain, our work was primarily on getting the framework moving and making sure the pipeline can work for a broad spectrum of items.
And we were, one of the things which we wanted to do was take some of the work that Free University had done in mapping particular healthcare and life sciences data sets. And we wanted to build on that as an initial mapping framework. So you'll see some of that with Christian.
Did you get any problem with the labels, like that it's ambiguous, that you can get flashes or something?
I had terrible problems with it.
Yeah. Yeah, because I ran into this same problem with the RDFIO extension. So then basically I tried to store the original URI as a kind of a basic identifier, because these are the only ones you can really be sure these are unique.
Yeah.
So maybe that should. And then you could even, I mean, if the label is not available, you could choose, you could have a set of properties that could be used as title in a prioritized order or something.
We do as well,
Yes, maybe Christian can speak to that. Yes.
Sure.
yeah. I'll have that in my talk later. Okay, so we'll continue from Will's presentation and explain sort of how we did this. This is if you've heard about linked data, this is like the obligatory slide. This is the linking open data cloud. So this is a massive amount of data that is available for free consumption on the web, and you can pull this into your wiki or application. And the nice thing is that data sources point to each other, so you can go from one to the next and use Wikipedia information, for instance, combined with biological data sets, and so get pictures from one source, get descriptions from the other, and get like side effects from another source that you really trust. So that's really nice in theory, but in practice it's not so easy. How do you get this into the wiki? You need to figure out a way to download all the data, keep it up to date. You're sometimes dealing with gigabytes, or sometimes even terabytes of data, which is not easy to work with, actually. Then data sources use different vocabularies. You could either work around that by writing Sparkle queries that account just for every vocabulary that there is, or that your source data is using, or you find a way to transform everything into one vocabulary that you defined or that you found somewhere that you like, which is what we're doing. And lastly, the issue that was just raised was how do you connect two entities identifying the same subject, and we have a solution for that as well. And our solution is called LDIF. It's a framework, linked data integration framework, and it aims to help you solve all these issues. What it does is it takes care of the data download and update as well. It helps you translate your incoming data into a vocabulary that you define. It helps you resolve URI or duplicates of URIs within your data and translate it so you have a single set of it has a function to look at the input data to generate a label. So if you have a resource called A12345, and it has a label aspirin, for instance, then our component, which is called Silk, allows you to generate an identifier name aspirin instead of the cryptic name. Finally, the output is written to disk, or it can also be written to a triple store, or quad store in this case. It's bundled with Enterprise TSC in combination with the SMW Plus link data extension. I'll have a few links to that on the last slide if you want to start using it. We also have a standalone version of it. And we're funded through Project Halo as well as Latitude. Now Andreas will give an overview of LDIF.
Okay. Here you see how LDIF was planned in the beginning. You see the publishing layer below. So there you have D2R, and there are like 3 types how RDF data is published on the web. And there are Slack endpoints. You can download a huge data set, which is just one big file. Or the most common type is you have URIs, which are dereferenceable, and which are linked to other URIs, and so on. For all of these methods, LDIF offers different access modules. For example, a crawler for the URIs. So it just follows links and gathers the data. Or a Spark access module, and so on. So on the third layer, you see the integration pipeline of LDIF. And okay, you already heard about the steps. It's a vocabulary mapping after the data access and the identity resolution and duplicates. There's one module which isn't implemented yet, which is quality evaluation and tries to clean the data a little bit up and tries to solve contradictions and so on. And with this integrated data set in the end, your linked data application can work. And in a very normalized, homogeneous way. So our current goal right now is scalability. Here you see our last benchmark steps. We used different data set sizes, which went up to 100 million triples. And this was all run on a single desktop machine. And as you can see, if you move on and go to the billion triples, then this won't scale on one machine. So we try to port LDIF to Hadoop and make it more scalable. But this is all still under development. So what I actually want to talk about is to introduce R2R and Silk. And if you have the problem to integrate data from the web of linked data, then what problems do you actually encounter, and how R2R and Silk help you solve them?
I didn't mention this, but these are the names of our components that do the transformation.
So R2R is vocabulary mapping, and let's start. So the most common problem, of course, is that you have class names or class URIs and property URIs, and of course in each vocabulary they are different. And so this is very easy to solve. You just rewrite them, and what you do is you in R2R you specify a source pattern and a target pattern, and which basically says that if you have an entity of type musical artist in the Wikipedia ontology, it should be considered as a music artist in the music ontology in the target. And R2R takes care about the rewriting for the instance data. So if you have the Wikipedia data set, you get out data which is represented in the music ontology. So the next problem is structure mismatch. Data which, for example, is directly connected in one ontology to the entity. For example, here in the textbook, you have executive branch head of government, which is like the leader of the country or whatever. which is represented in Wikipedia are kind of more complex. The leader name itself is an own resource, which then is linked with fourth name to the actual value. And what you do, you just describe again the patterns, the graph patterns, and how these different nodes correspond to each other, which is here marked with the different colors. And R2R will rewrite these more complex patterns to the more simple ones. And then there are what we call modifiers. You may have the problem that there are different data types in the different ontologies, or that some values are represented as URIs in one, which are then represented as literals in the other ontology. And this takes care of the conversion. Okay, another problem is schema mismatch, where, for example, you have a class in one ontology. Here it's a singer, so it's a music singer. And in the other ontology, there is not really a single class. So we have here the music ontology, there's just a record. And what they do is that there's also a property release type, which differentiates the type of the record. So in this way you have an instance in the music ontology called single, and this would be the value of the release type property in this case. So to map this case, if you go from the music ontology to the Wikipedia, you would just restrict all the entities of the record class and just say, yeah, the release type should be the instance single. If you want to go the other way, that would mean that you generate two triples out of one. So you would have an entity of type single, and in the other ontology you would generate two triples, one that would say that it's of type record, with this extra triple for the specific type. And one problem that actually appeared very often in the Neurowiki use case, you want to extract values out of other values, or in this case, out of a URI. So the relevant values we want to have is this one. It's just the ID we want, which is represented as a URI in the KV ontology, and it's only the last part of the URI. So we specify a transformation to cope with it, which is basically in this case a regex, which filters out the relevant parts. And here you also see a modifier, which modifies the target value to a string value. So Silk, as you know, is the identity resolution module which finds duplicates. And I will show some examples which introduce the main parts of it. What's the core item of Silk are linkage rules, where you can exactly specify when two different entities should be considered the same entity. And what you do is to define similarity scores, which are between 0 and 1, and where you specify how the similarity score is computed. And you also specify a threshold, and all matches above this threshold are then considered to be the same entities. So some examples. Let's say we have mainstream music bands, and in the mainstream it's usually the case that band names are trademarked. So you have unique band names, and this use case would be very easy because you just check for equality. If one band name in one data set has the same name as a band of the other data set, you can say, okay, this is the same band. So the outcome would be 0 or 1. It's a similarity score, and that's it. So the threshold would be 1 actually. So, but, okay, there are other comparators. There are string-based similarities, token-based, or, for example, data types. If if you want to compare, for example, Berlin, there are a lot of Berlins in the world, like, I don't know, 30 or more, and especially in the US. This would be a way to differentiate these different Berlins. You could say, okay, if there are two Berlins which are very near or close to each other, you do this with the geocoordinates, then you can say, okay, this is the same Berlin. Okay, let's move on with the band use case. Let's say you also want to integrate all the local bands from the globe. And as you may know, local bands don't really care about trademarks, and they often have the same name, of course. So it wouldn't be enough to compare just the band names. So we add a comparator. In this case, we look at the band members and their names and see how much overlap there is between the names of the band members. And since you have now two comparators, all these similarity scores have to be aggregated somehow to one single score. And in this case, this is just known as an average. And yeah, the new threshold, of course, should be above 0.5, because as those all already match the band names the same. We don't want to. Okay.
Okay, thanks. Now I briefly want to show how this all works together in the pipeline.
Can I ask a question first?
Yes, sure.
Yeah. I was wondering, have you tried to learn rules automatically?
That's what we're going to do. That's usually stuff.
In general, how does it compare to, I mean, I think the overall task here is ontology alignment, find same entities in different schemas, and there's a lot of work on that, competitions. Do you see yourself in that space, or is that distinct now? Do you participate in these competitions?
I think we will participate in the space, but right now we don't learn the rules, which are the main aspect right now.
Yeah.
And we just wanted to have a very simple mapping language, which is simple but still can cope with most use cases.
But it's based on everything has to be done manually, so if you have
Right now you have to write the
manually.
Well, it's not true for Silk. For Silk, there's already a learning mechanism.
Yeah, but I mean, it's still useful a bit because, obviously the vocabulary is much smaller in most cases than the number of instances, and rules happen on the level of vocabulary.
Right now you are only supported by an editor, which Christian will talk about. So, any more questions?
How do you do, maybe you will talk about that, how do you pattern matching? Is that by Sparkle or all?
Pattern matching?
Like, you need to do some pattern matching for doing these mappings, I guess.
The execution. Just execution. Yes, this can be done with Sparkle, and the first implementation of R2R worked against Sparkle endpoints, Sparkle 1.0. But right now we have an own implementation which only handles the subset of Sparkle to make it scale more.
Okay. So we combined this into a pipeline in order to support those use cases, or use cases like this. And it's basically run in 4 steps. Steps 1 is collecting the data. Step 2 is mapping it to the local schema, so executing R2R. Step 3 is resolving duplicates or importing external identities into our target. Step 4 is outputting it or saving it or populating it. Right now this process is run in parallel on one machine, but we're working to distribute it across multiple machines. Data import. We support pretty much all RDF formats, including compression, so you can actually give it a compressed URL and it will download that and decompress it on the fly. Sparkle endpoints, as well as linked out data crawling, which means you can give it a DBpedia URI, for instance, or for that matter, maybe category band names, and tell it, okay, look up all the links you find in that page. Or download all the data you find referenced from this page. And I will show this in the context of Neurowiki. How it works. So in Neurowiki, the data sources are defined on the wiki page using special templating syntax. This is how it looks in the end when it's parsed. So here you see, for instance, these are HTTP dump URLs, and this is the source for it. So it's a rather simple template. In the standalone mode, we have XML configuration. Once you've done that, you can go to a import status page, which lists you all the data sources that you defined. The date of the last import, whether it was successful, any error messages or warnings, and you can rerun the import or run an update on it. It's a bit, well, could be more, but it does the job for the time being. So it's the import portion. Then we have R2R, which does the schema translation. So to repeat, for instance, I have an external data sources that talks about genes that are referencing pathways. And in my wiki, I call them wiki:gene, and instead of saying has pathway, I would like to say is involved in something. And to do that, I define mappings in the R2R language. To assist the user a bit with this, we created an editor, which is also integrated into the wiki. So this lists all mappings defined at the moment, and I can go in and edit it. And it shows me that I'm mapping two classes, disease and genes, and some properties associated with them. And I can go into each of these and show me the mapping rule that is behind it. So, for instance, here I'm simply matching labels, or I'm converting labels. I'm applying a transformation to the label, and yeah, we have an editor with a function reference, and so we try to take the pain out of editing this a bit. But this is how it looks internally, how it's generated. So that should be enough for this.
You call it the R2R language?
Yeah.
Kind of an extension of Sparkle also?
No. It does support, like in the source pattern component, like the input component, it supports most of Sparkle syntax. So if you're familiar with Sparkle, it should be fairly easy to work with. Okay. The next step, the identity resolution, again, is to help you if you have multiple instances that are the same. Silk helps you to find them. I also have the example from multiple build-ins. How do you find the right one? The best way would be to look at geographical distance. For that, we have what's called the Silk workbench, which is also integrated in the wiki. Again, it shows me a list of linking profiles that are set up, and I'll just show one example. This is about resolving genes in Neurowiki. And when we resolve genes in Neurowiki, we want to, or when resolving genes, you have a lot of different identifiers. You have multiple authorities that each assign IDs, and we found out easiest and the simplest way to harmonize genes that come from multiple data sources is to simply compare those identifiers that various authorities assign to them. So this is what we do here. This is a graphical representation of the Silk mapping rule, similar to what Andreas mentioned. The way it works is you have an input source, an input predicate, an output, a predicate from one data source, a predicate from another data source, and then you run comparisons on it. In this case, it's a simple equality comparison, so 1 or 0. We do this for a total of 4 properties, 3 properties, and then aggregate the results to take the maximum, I think. So if any of these matches, we generate a link. And this editor gives me shows me my ontology, which is defined on the wiki on the right hand side. So if I wanted to add another reference to this, for instance, add another uniprot comparison, what I do is I drag these onto the editor, then I can add a comparison. So and I can connect it up. Okay, that's so pretty. Okay. And these can get quite more complex, but we'll leave it at that. Finally, output. We can output n quads, which is like n triples, but with a graph reference, n triples, and also we can write to Sparkle stores. Any data that we output, we want to include provenance, which means information about where did we get this information from, and when did we get it. This is quite useful because if you're working with your own local schema, you will lose, you will ultimately lose some information that you had in the first place, or that is in the original data source. So we provide for ways that allow you to get back to the original data. Any questions at this point? Yeah?
So this whole LDIF, is it run like, what is the implementation, PHP or some other system?
It's implemented in Scala.
Okay.
So it's binary compatible with Java.
But you control it from inside of the wiki, or you run?
Yeah, you control it from the wiki. We have PHP bindings in the wiki. Yeah.
Cool.
I think that layer just probably write the data into the file, right?
This was also, the controllability in a wiki was also a requirement. We wanted to ensure that all the mappings were transparent to the scientists and could be edited in the normal wiki way and maybe achieve consensus that way. And so rather than have it in a separate application, we wanted it, again, to be completely embedded in the wiki, so that not only when you're looking at one of those fancy queries that we'll show, you could actually trace back through the mappings, if you're a scientist, to the original data sources, which was one of their absolute requirements.
Yeah.
Do you see different use cases besides the number scientists, or use cases present for the
Yes and no. The Linked Data Cloud definitely gives way for many more use cases. But what we're actually looking for are people with concrete problems where this may be a solution. So it's a rather new technology. I mean, we had the first official release in June. And so we are actually, I think it's a bit of chicken or an egg problem. we have a solution, and now we're looking for people to, with problems to use it. So I'm not. Well, I'm aware of many cases. This, for instance, this is being, or parts of this are being used in the LITC project. Maybe Anna can elaborate on it. And there, the goal is actually to sort of lower the limits of linked data application, lowering the limits of using linked data. So one of the things they do is they create lots of links for you, and they will publish them. So this is where this comes in, being helpful as to who it will, who will benefit from it. Ultimately, I don't know at this point. So,
It wasn't clear to me in what cases the data is being actually imported into the wiki as wiki text, and in what cases it's just being queried.
Okay.
Yeah, could you?
Yeah. So our pipeline actually does not import it into the wiki.
Okay.
Rather, it imports it into the Enterprise Triple Store, from where it is then accessible in the wiki. And Will's page creation bots actually work on top of that data.
Creating the pages and inline properties.
Okay.
So basically the Triple Store has a ton of information, more than I ever need to put on a wiki page. And we take that information with our Sparkle, place it into the wiki pages in the embedding, and then that creates the ontology for the wiki user. For the ask queries, for the facet searching, for basically all the semantic pieces we made. It's just a way of scaling down how much stuff I have to put into my SQL database versus what's usable. There's nothing changing it from me embedding more or pulling more in on request. It's just a usability function right now. Where useful data is prioritized to go into the wiki.
You mentioned it's pretty new. I'm just a bit struggling still with the exact workflow of this. So you, from data you gave, it takes about 10 to 80 minutes on a medium-sized data set, medium-sized by current standards of how large the web of data is. Now, so this means it has to be done in batch mode, so you don't see immediately what happens if you change the mapping rules.
Exactly. Yeah.
Also, on the other hand, you have the need to have some implicit mappings in the rules. For example, you gave the example of comparing coordinates to find out which burdens are the same. But if you have different data sets, then surely also the property used to say what a coordinate is, and even the format maybe of the coordinates is different.
Yeah.
So these rules implicitly also, if you make a rule like that saying if the coordinates are similar, it's the same. They also have implicit information which coordinate properties are to be considered the same. And this seems to, this may affect many rules, and if you change your mind on that later on, it seems to be a bit unclear how the workflow would be to find all the rules that are affected by this change in mapping, and how to see if your updates do the right thing, if it always takes a long batch process. So how exactly does that work out in practice? Do you normally not change the mappings after you did it once, or
we
a cycle of doing it, or what do you
well,
do?
what we do is we work with subsets of the data. So once you have even one instance with obviously with all the data that's connected to it that you're interested in, you have pretty much everything you need to write these mappings and to test them. So,
but when you write them in the wiki, how do you test them? Does it happen automatically? You just wait for 10 minutes and then you see what happens, or
no?
Is it lightly, or do you trigger it by a button, or?
No, you at the moment you have to manually trigger it.
Neurowiki works on triggers right now.
Okay, right.
In the interest of eating lunch, how about we answer questions outside?